Welcome everyone. In this video, we are going to discuss the SCION public key infrastructure, or PKI for short, in more detail. The PKI is concerned with the authentication of network entities, be it an autonomous system, a web server, or an end domain. SCION offers exciting approaches for highly available and highly secure PKIs. So let's take a closer look at the principles and mechanisms we introduce to achieve these properties. I'll start out by providing some PKI concepts first. PKI stands for public key infrastructure, and the purpose of PKIs are to enable authentication of an entity. So what's an entity? There are many different types of entities. So for instance, an autonomous system, which could be an ISP, an internet service provider, or a university or a corporation. Essentially, you can imagine one network that is under administrative control of one entity. A router could be also another entity, or a service, or a website could be one entity. So in essence, we want to authenticate one of these entities, and the PKI helps us doing that. Other important terms that we're going to make use of is the term of certificate, and a certificate binds an entity identifier to a cryptographic key. I should also say cryptographic public key. A root of trust then is an axiomatically trusted entity to start the authentication process. So it's essentially all the base public keys that you trust to perform the subsequent authentications. And a certification authority, a CA, is a trusted entity that issues certificates. So with this background, let's now take a look at the desired PKI properties. We have the following properties we'd like to achieve. The first is trust scalability. So we'd like to support heterogeneous trust relationships. And as our world is a complicated place, there is no single entity that is uniformly trusted by everyone. Sometimes I joke, even Switzerland is not trusted by everyone. So in essence, we'd like to have a system that can support such heterogeneity in the trust relationships where different entities would have different roots of trust. Next, we also seek transparency. And there are many different aspects of transparency. The first aspect has to do with the roots of trust. We'd like to be able to enumerate all the roots of trust that one has to rely upon for certain operations. The second aspect is accountability. So we'd like to be able to hold all the operations that a public infrastructure performs accountable. Next, we'd like to be resilient to trust root compromise. And as we know, different entities sometimes make mistakes, and we've seen this in many cases in today's world. And we'd like to build a system such that the system provides some level of resilience to malicious CAs or malicious entities that have compromised the root of trust. Next, once a root of trust compromise does happen, we'd like to be able to quickly recover from it. And finally, we want trust control and agility. So in essence, entities can select which roots of trust they want to rely upon. And here with entities, I mean even end users or domains or autonomous systems could decide which trust roots they want to rely upon. Also, hosts can select which trust roots they want to rely upon for verification of certificates or other entities. In this video, I'm going to overview 3 different PKIs that SCION introduces: the control plane PKI, the end entity PKI, and the name resolution PKI. And I'm also going to briefly talk about the DR key system, which we'll additionally discuss in a separate video. So let's start out with the control plane PKI. As a quick reminder, the control plane is the system that determines and disseminates end-to-end paths. And we have a separate video where we discuss and look at an overview of SCION's control plane. The interdomain control plane in the current internet relies on protocols such as the Border Gateway Protocol, BGP, or the protocol, in addition to ICMP protocol, as well as other support protocols. The control plane PKI mainly provides AS-level certificates to enable authentication of these autonomous systems. And so the main requirement that we have for this control plane PKI is very high availability. So in essence, we want to be able that the PKI works without having to rely on the availability of being able to communicate with different PKI servers. And this is to avoid cyclic dependency issues between routing and PKI operations. So imagine receiving a routing update message, which you need to be able to trust in order to be able to communicate with end hosts. If you would need additional communication in order to verify this routing update message, then the question becomes, how would you verify the first routing update you receive, in which case you cannot really communicate with anyone else in the internet. And so avoiding these types of cyclic dependencies and achieving very high levels of availability was one of the main aspects in order to design the SCION control plane PKI. Next, I'll briefly discuss how we achieve the property of trust scalability, and isolation domains are the main ingredient to achieve this. And our observation is that a subset of the internet can agree on a root of trust that they want to rely upon. And in essence, the isolation domain then becomes a domain in which a certain set of trust roots are active in. We're going to authenticate different entities within each isolation domain, and both users and domains can select which isolation domain they want to rely upon based on the root of trust that is active within this isolation domain. And this approach can also support modern PKI approaches, such as certificate transparency or the attack-resilient PKI, which we also make use of in SCION. The challenge of splitting up roots of trust in this way is to retain global verifiability, and we see in a minute how SCION can achieve this. A core ingredient of the SCION infrastructure is the trust root configuration. So each isolation domain defines trust roots within a trust root configuration. And the trust roots encompass the three PKIs that SCION uses, the control plane PKI, and the core AS certificates that constitute the trust roots for that control plane PKI are part of this TRC. Also, the trust roots for the end entity PKI, the root CAs, as well as log server certificates are part of this trust root configuration. Also, the root name server certificate, which is crucial, and the root of trust for the name resolution PKI is as well in that file. This TRC achieves a property called trust agility. So hosts can select which ISD and which TRC that is associated with that ISD they want to use for verification. TRCs also enable efficient updating of trust roots, as we're going to see in a minute. And I'd also like to point out that this distribution of TRCs is tied to path exploration and resolution, which we're also going to see in a subsequent slide. So as SCION beacon messages are being sent out in the path exploration, the updated TRC versions are being pushed as well, and updated TRCs are being fetched as a result. So in this slide, we see a sample TRC. In this example here, we have three different control plane PKI routes. So this isolation domain would have three core ASs that manage the ISD and their respective public keys and represent the roots of trust for the control plane PKI. We also have identity PKI routes, root CAs, that are listed here. In this example, we have a VeriSign, a GeoTrust, and a DigitCert certificate. We also have identity PKI logs, which I'm going to explain later in this video, as well in a separate video that is specifically on the entity PKI. The root of trust for the name resolution PKI is listed next. And finally, we have cross signatures by neighboring isolation domains that we're going to see in the next slide. So in essence, each ISD that connects to a different ISD signs the other ISD's TRC. And as a consequence, we get a nice property that whenever a networking path exists, we also have a valid verification path from the source to the destination. So here's how this works in a bit more detail. So the TRC verification essentially follows a core path. And in this example, we have the purple ISD and the path all the way to the green ISD. And in this case, we have two different paths, one going from purple to red to orange to green, and one going also taking a detour through the blue ISD. So in this example, if one trusts the purple ISD and the purple TRC, in order to verify this, the green TRC, one can follow and first verify the red TRC, the orange, and then the green. Essentially just follow this chain. In addition, ISDs can also cross-sign each other's TRCs without being directly connected. So in this example, you see the dotted line. The purple ISD can also sign the blue ISD's TRC, and the blue ISD's TRC can sign the green ISD's TRC without being directly connected. So as a consequence, we have two independent verification paths which can offer additional levels of security if both are being verified. Next, let's take a look how we can update TRCs. So consider this setting here where we have the blue ISD with its current TRC, and now a new TRC is being created. So perhaps some parameters within the TRC were changed, or a root of trust of the TRC is updating its key or has been compromised. And so the previous roots of trust can now sign the new TRC. So new TRC is being created, and it's signed by the prior roots of trust. It can also be cross-signed at this point by other neighboring ISDs. However, that's not strictly required, and the operation is feasible and possible to update purely with the blue ISD's entities. Now, what happens is, as beacon messages are being transmitted, the current TRC version number is also embedded in the PCB, in the beacon message, and a receiving autonomous system that does not know that new TRC will go back and fetch that TRC from wherever it received the beacon message from. So as a consequence, the new TRC very quickly is distributed across the whole network, and so the entire ISD has updated the TRC within a few seconds. Also, what's important here is that no additional circular dependencies on the communication and the TRC verification is required, because the new TRC is being sent across the same links at which beacon messages are being received. No additional communications outside are necessary to receive and verify the TRC. So next, I'll talk about AS certificates. So each AS can obtain a certificate that's signed by a core autonomous system, a core AS. And so again, the same problem we discussed so far exists, that the revocation check of a AS level certificate could introduce a cyclic dependency between the control plane and the PKI operation. So as beacon messages are being sent, each recipient wants to make sure that all the certificates from the ASs that have signed that beacon are valid and uses those certificates to verify the beacon. And again, we don't want to introduce any cyclic dependencies. So what we do is we use short-lived certificates to avoid the requirement to contact an additional server to verify such beacon messages. And currently we use short-lived certificates for all the non-core ASs, which are valid up to 3 days. Core AS certificates can be revoked through TRC updates, and so for those we have longer validity times and don't need to use short-lived certificates. So any autonomous system can now certify another autonomous system through the chain of cross-signed TRCs and verifying core AS signatures. And also the certificate distribution is tied to path exploration and resolution. So in path exploration, as beacon messages traverse the network, each entity fetches all the certificates that are required to verify those beacons. Similarly, in path resolution, the path servers that obtain either up paths or down paths fetch all the certificates that are needed to verify these up and down path segments. And as a consequence, through path resolution, all the AS certificates are being disseminated throughout the network. So let's take a look at an external ISD AS verification. So consider you're in a purple isolation domain and you trust the purple TRC. Now, in this example, we want to verify a certificate by the green AS E prime within the green ISD. And so we want to verify a certificate of E prime. To perform this verification, we essentially follow a core path from the purple ISD to the green ISD. So we can go and first verify the red TRC, then the orange TRC, and finally the green TRC. And once we trust the green TRC, we can now verify the certificate of E prime as it is signed by one of the core ASs or one of the roots of trust within the green TRC. So again, notice that any networking path will enable such verification. Also, multiple paths can be used to verify these TRCs. And in this example, the blue TRC can be used in addition to verify the orange TRC. If we look at the desired PKI properties we looked at previously, we see that SCION's control plane PKI achieves all of them. So we have trust scalability, which means that we can support heterogeneous trust relationships, which is achieved through the use of isolation domains. Also, transparency is achieved because thanks to the TRC files, we know exactly all the roots of trust that are feasible. And so it's very easy to enumerate all the trust roots. And also all PKI operations can be accountable in this environment. We also have resilience to trust root compromise because we can quickly update the TRC and quickly push this TRC through the network and thus achieve also quick recovery from compromised trust roots. The TRC file itself needs to be signed by multiple core ASs to be updated. And so a single malicious core AS is insufficient to update the TRC, and thus we also get this resilience to compromised roots of trust. In terms of control and agility, an AS can decide which ISD it wants to be part of, as well as hosts can select a TRC that they want to use to start their verification. So next we'll look at the DR key system, which is part of this control plane PKI. And DR key stands for dynamically recreatable key. So in essence, our AS certificates that are part of our control plane PKI can be easily used to set up and bootstrap authentication and secrecy by using the public keys to establish shared secret keys as in a protocol like TLS. But unfortunately, asymmetric key cryptography, also to set up these keys, is quite slow in practice and would not work very well for the following cases. So consider a router that wants to send an authenticated error message to a remote autonomous system. Or consider an end host that wants to encrypt a secret value to send to a router on the networking path. If one would have to perform asymmetric operations for each of these cases, a router could not very efficiently create these error messages, or end hosts and, again, remote routers would have to perform asymmetric operations for establishing keys. So we want to avoid these cases and make key establishment very, very simple for routers and very efficient. And so the goals that we have in DR key is to enable rapid establishment of a shared secret key between any two entities so that routers can very quickly and efficiently derive per-host secret keys without any per-autonomous system or any per-host state. So it sounds quite magic, so let me give you a high-level overview of how this works. Again, the details will be coming up in a future video. So here's how DR key can be used to derive AS to AS symmetric keys. So the basic idea is to use a per AS secret value to derive keys through a pseudorandom function. Imagine each AS having one of these local secrets that they then use with one of these PRFs, a pseudorandom function, which can be implemented, for instance, with a block cipher. So here's an example. So we have an ASX that desires to create a shared secret key with ASY, and it has a local secret value that we call SV sub x. And so we denote the key, the symmetric key from ASX to ASY with this notation K sub x arrow y, and it's computed with secret value x applied to the string y using the pseudorandom function, essentially for which we use a block cipher. And using the AES-NI instruction set, we can compute this PRF within 50 clock cycles on an off-the-shelf Intel CPU. So the observation here is, which is quite exciting, is that the key computation can be even faster than a in-memory key lookup. So a memory lookup to DRAM, assuming it's not cached in one of the CPU's caches, can take up to 200 cycles. So by recomputing the key dynamically, we can be 4 times faster than the memory lookup. And so this is an aspect that is quite exciting to us. So, and DR key exactly utilizes this concept. So now consider any entity in ASX that knows the secret value X can now derive any key for any other autonomous system on the fly. So imagine the router inside ASX. So it needs to now create a key for ASY to verify, say, an SCMP message, which is the SCION control message protocol. So we can now derive a key X to Y on the fly, as we have shown on this slide. And now the question, though, is how can the destination now obtain this key? Because the destination does not know the secret value X. It turns out, and again we will describe this in a subsequent video, ASY can ahead of time fetch all these shared keys of other ASs that are shared with it. So ASY would contact ASX to fetch key KX to Y. And now this is a slower operation, but it only has to be performed, say, once per day. And now, based on this local key that ASY has fetched, it can now verify any error message that was sent by any router in ASX. And what's important here is that the router operation is very, very fast. So the router only has this single key SVX, single secret value X, and it can derive keys for each other autonomous system on the network. All right, next we'll talk about the end entity PKI and the name resolution PKI. So if you look at the properties of the current TLS public key infrastructure, you see that it doesn't achieve any of the properties that we seek. It doesn't achieve trust scalability because it cannot support heterogeneous trust relationships. If a user or an entity decides not to trust the CA, all the entities that are authenticated through the CA cannot be authenticated anymore. And therefore, there's no real notion of trust scalability that can be achieved today. Also, with respect to transparency, it is actually not possible today to enumerate all possible trust roots. The reason for this is that secondary CA-level certificates can be signed by primary root CAs, and the second-level CA certificates can also be used to again sign domain certificates. These are essentially invisible, and therefore one today cannot enumerate all different roots of trust in this environment. Also, there is no accountability of PKI operations. Root CA can sign a certificate without it being visible to the rest of the world. Moreover, the current system has no resilience to trust root compromise built in. In essence, if a CA is compromised, arbitrary certificates can be signed, and we have seen examples of this happening in the world. There's also no quick recovery from trust root compromise. We've again seen examples of compromised root CAs where the recovery included a browser update or an operating system update that needed to be installed, which can take on the order of days or sometimes even weeks for most users to take care of. Finally, with respect to trust control and agility, an entity cannot really decide which trust roots they want to rely upon. In essence, everyone has to rely upon all the roots of trust in today's internet, as well as all secondary roots of trust which are invisible. So, moreover, hosts cannot select which trust roots they want to mainly use for verification, because if a host or a user deletes some of the roots of trust, then all the entities that were certified by those roots of trust cannot be authenticated anymore. So in essence, we achieve none of these properties in today's environment. Fortunately, an improvement has come with certificate transparency. And so Google has suggested certificate transparency and has also leveraged its market leader position to improve the security of the TLS PKI ecosystem. Chrome has currently a browser market share of about 60%. And so with this base, Google was able to push certificate transparency in a way that current CAs become compliant with the system. And what certificate transparency adds is essentially public log servers that create a public ledger on which all valid certificates are being logged. If a certificate does not appear in any ledger, it is considered to be invalid. And Google has made CA compliance with certificate transparency mandatory by October 2017. So this is really a huge advance over the current state of the art, and it's a really great system. But unfortunately, certificate transparency only achieves the transparency properties. It becomes possible to enumerate trust roots, and it creates accountability for PKI operations, but it does not help with trust scalability or resiliency to trust root compromise, as man-in-middle attacks, etc., are still possible. The recovery from trust root compromise also is not much quicker, as well as entities can still not really rely upon certain trust roots they want to rely upon, and also hosts cannot really select which base trust roots they want to use for verification. In the quest to increase the security of the TLS PKI, many systems have been proposed. And so basically, the man-in-the-middle attack, where an adversary creates a new bogus certificate to attack a service or end user, needs to be prevented. And so the idea is to cross-validate TLS certificates with multiple entities. And so the perspective system by Wendland et al. Was a system that provided a network of notary servers to record certificates from multiple vantage points and report these to browsers. And essentially in perspectives, if a certificate has not been seen by the network of notaries, then a certificate was not trusted. And this also added a notion of transparency to the whole TLS PKI. Subsequently, certificate transparency and sovereign keys by Laurie et al. Or Eckersley, respectively, have proposed this public ledger of log servers which contains all valid certificates. And this is the system that Google is now proposing and promoting, which provides a big advance in the state of TLS security. However, relatively few of the properties that we seek are being achieved through the basic system. The attack-resilient PKI by Basin et al. And the Polycert system by Szalachowski et al. were proposals that we made as part of the SCION project, which we're including in the end-to-entity PKI that I'm going to present next. However, in this talk, I'll only present a high-level overview of the system, and there's another video by Paweł Szalakowski that explains ARP-key and polysert in a lot more detail. But let me give you a brief overview of this end-entity PKI. And essentially, SCION's end-entity PKI is based on this attack-resilient PKI and polysert. And in this environment, we have two different certificate policies. We have a subject certificate policy, which is per domain, which essentially lists a domain's certificate policy. Then we have multi-signature certificate, or MSCs, which then are similar to current TLS certificates, which are typically signed by multiple entities, but also signed by a key that is defined in the subject certificate policy, or SCP. So the basic observation that we followed in this end-entity PKI is that the domain subject certificate policy would change very infrequently. So we put in a lot of effort to secure it, and with quite expensive operations. But then the multi-signature certificate, or the MSC, which is created much more frequently, relies on the security of the SCP, but can be much more efficiently updated and replaced. So in essence, to give you a brief flavor about how SCP registration works, it uses notions that are similar to certificate transparency by Google, in the sense that a CA that creates one of these SCPs needs to log the SCP at a set of log servers. And these log servers are all synchronized to make sure that they see a consistent view of all registered SCPs. And also multiple CAs can sign these SCPs. So in the end, the SCP then is used to sign MSCs that provide then the actual certificates that the domain uses in practice. So in the SCION end-entity PKI, the TRC contains the trust root of CAs and log servers, as we've seen earlier in this video. It also contains a parameter that can be selected by each isolation domain, which represents a threshold of different signatures that are required to create an SCP. So for instance, one ISD can define and say every SCP has to be signed by at least 2 or 3 different root CAs. And then the SCP defines a domain-specific policy, which can list the trusted certification authorities, the trusted CAs, within the given isolation domain, and also a threshold number of signatures that are required to create an MSC. So the SCION end-entity PKI achieves quite an exciting security property. So consider that the domain D has an SCP and MSC registered in ISD-A with TRC-A. So in this case, the important property that we can achieve is that any client that uses the TRC-A as its root of trust can be assured that, and can be guaranteed, that at least a threshold number of trusted entities that are defined in the TRC-A must be malicious in order to forge a fake SCP or MSC. This is, again, a very strong property that cannot be achieved in today's environment. One aspect that is necessary to verify SCP or an MSC has to make sure that if the SCP has not been registered by TRC-A, but in an external ISD with an external TRC, then this client needs to obtain a proof of absence that no SCP is defined within the ISD-A. And so this shows that this approach will require additional overhead. However, the security property achieved is very strong. So in conclusion, for the end-to-end PKI, the SCION and entity PKI achieves all these properties. So again, trust scalability is given by the use of isolation domains. Transparency is given through the log services, where it's possible to enumerate all the trust routes which are listed in TRCs. And also, all PKI operations become accountable thanks to the log servers. We also have resilience to trust root compromise, because one can specify the requirement for multiple signatures on SCPs or MSCs. And so any single failed CA or any compromised key cannot be used to create fake certificates. There's also quick recovery from trust root compromise. If a root CA or a trust root is compromised, the TRC file can be updated and very quickly pushed through the whole network. Also, trust control and agility is given, as entities can select which trust routes they want to rely upon. So a domain, through the use of SCPs, can select that they want to rely on certain routes of trust and not on others within that ISD, as well as hosts can select which trust routes they want to rely upon for verification. Essentially, hosts can select an ISD or TRC that they want to start the verification with. So I should also say briefly that if a domain does not want or does not need high level of security, it can actually also select not to have a SCP and simply have MSCs that are signed by a single CA. So similar to today's environment. But another entity who wishes a high level of security can select and register its SCP and MSCs with parameters that match the desired level of security. So next, let's talk about the name-based PKI. And for this, we'll first briefly talk about the DNSSEC-based PKI. So one idea is to use DANE, which proposes to also include domain certificates as part of DNSSEC. This looks like a great idea initially. However, there are several problems with this approach. So the main problem we see is that all entities on the verification chain need to be trusted. So the whole system is only as secure as the weakest link. If one entity controls a key or there's a compromised key that is used in the verification chain, all the entities below that point can be forged, or certificates for these entities can be forged. And so the level of trust is really quite weak. Such systems can also introduce a kill switch, where the revocation of a key can invalidate all entries that are below that point in the tree. And so if we look at the PKI properties with respect to DANE, we see that the only property we get is that it's possible to enumerate the trust routes, but also there are very few trust routes in this case, and that makes the system quite vulnerable, and the security is only as good as the weakest link. In contrast, the SCION name resolution PKI uses two different verification paths. It also uses a verification path that is similar to DNSSEC, so that has the same disadvantages. However, in addition, we use the SCP of the end entity PKI to also digitally sign a domain key that is then used to sign the DNS or the RAINS entry. RAINS is the system for name resolution that we use in SCION. And so essentially we use the name resolution PKI for high availability, but then we use an SCP to achieve high levels of security. And again, if a domain decides that they don't need a very high level of security, they don't need to register an SCP, and they fall back to the level of security of essentially basic DNSSEC. So the combination of these systems again achieves all the properties we seek. We have trust scalability, thanks to the isolation domains, transparency, and those are inherited from the end entity PKI. We also get resilience to trust root compromise, again, from the end entity PKI, and again, quick recovery from trust root compromise thanks to the TRC dissemination mechanism. Similarly, entities can again select which trust roots they need to rely upon, thanks to the properties from the entity PKI. And again, hosts can select their trust root for verification by virtue of being able to select the TRC. So in summary, SCION integrates three innovative PKI systems. So the control plane PKI offers very high availability with very simple operations. The TRC provides transparency of trust roots, control, and easy ways to update roots of trust. And the DR key system that is connected provides highly efficient and scalable symmetric key derivation that can then be used throughout the network. Our end entity PKI uses a different trade-off. It's not as efficient as the control plane PKI, not as highly available, but in turn it offers a very high level of security where several trusted entities need to collude or be compromised in order to create a bogus certificate. And so it's the first PKI that we are aware of where a domain can limit the set of roots of trust for the certification of its certificates. And the important aspect here is, though, that what is required is a proof of absence in case an entity is certified by a TRC or by an IST that is outside the set of trusted ISTs or TRCs. Finally, our name resolution PKI offers a DNSSEC style verification, which is only used for availability, and then the end entity PKI can be used in addition to achieve a very high level of security. Now that you have heard about the SCION PKI, I invite you to view the next video by Paweł Szałakowski, which explains the SCION end-to-end PKI in detail. For more information, please visit our website. Chapter 4 of our SCION book discusses the material we've seen in this video in more detail. You can purchase the book from Springer Verlag, or you can download the PDF from our website. Thank you for watching.